Greetings and welcome, internet friends. Mr. Waddy here, looking at Alg2.10.04 probabilities of disjoint and overlapping events. Aha, so here we go. Here's some exploration problems. I think they'll help us quite a bit in understanding these concepts, but feel free to skip ahead to the examples if you'd like. So for problem A here, let's see, actually, oh, do I have colors? What colors could I use? I've been using green and purple a lot lately. I guess I'll use orange and red. So for event A, let's say I'm rolling a die. They want me to draw a Venn diagram, so that's what I'm doing. It says the result is an even number, so probability result is even. Yep. All right, and so even. And possible outcomes of that would be, well, actually, let me read the other one. And then the next one is the result is prime. Could even numbers ever be prime? Yes, there's some overlap there. And so event B would be prime. So let's figure out what numbers go where. So, well, the possible outcomes are 1, 2, 3, 4, 5, 6. 1 is neither even nor prime. Right? So 1 is somewhere out here. 2 is both even and prime. 3 is prime but not even. 4 is even, not prime. 5 is prime, not even. And 6 is even and not prime. All right, and so there's a little Venn diagram for problem A. Over here, let's draw one for problem Bravo. All right, and so so notice this one had some overlap. Here, the first case is the result is 2 or 4, and then event B is the result is an odd number. And so for event A, I'd have 2 or 4. Event B are odd numbers. Now, will there ever be any odd numbers that are either 2 or 4? No, it's impossible. Impossible. And so odd numbers would have been the outcomes 1, 3, and 5. And then were there any numbers that weren't in either category? Looks like 6. So 6 would just be floating around here. And so one of the things to be aware of here is that these two events had overlap, and hence we'll call them overlapping. And these had no overlapping. They were never joined. They are disjoint events. All right, and so depending on these two scenarios, based on the reality of the possible outcomes we're considering, it's going to result in different types of Venn diagrams and different kinds of probabilities. And so for event A, all right, here's exploration 2. It's talking about the same thing. They said, what's the probability of event A occurring? Event A here was any even, and notice there are 3 evens out of 6 possible outcomes, so that's a half. Meow, 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 meow. What's the probability of event B occurring? So that was primes, which was 2, 3, and 5. Happens to be 3 successful ways that could occur. But notice that's a different 3 than these 3 were. And then let's see. Now, what's the probability of A and B? So were there any outcomes that were both of those things at the same time? Well, it was just 2 to the number, which was a single outcome. And so 1 out of 6 ways. And then this is the new question. We've done probabilities of A and B before, but we've not dealt with OR logic. And so the probability of A or B well, it would be all of, actually, oh, here, I'll do it in green. It would be all of this. It would be all of this. Now, the problem is I can't simply add all of the evens probabilities, right? I can't take a half plus a half and get 100% because that doesn't describe it. One of the challenges is right here. This overlapped region would have gotten counted twice if I added the 1/2 and 1/2. And so that's where there's going to be a little bit of a nuance between overlapping versus disjoint events and their probability. So with this, I had 3 outcomes here and 2 more. It's a total of 5 possible outcomes. So 5 out of 6. It wasn't 100%. Let's consider these probabilities for part B. And this one I won't have to scroll back and forth. So what was the probability of event A in part B? Well, that was 2 or 4, and there were 2 possible outcomes. So that's 2 out of 6, or 1/3. Probability of event B is 1, 3, or 5. It was it odd? I think it was odd. Yeah. There were 3 of those outcomes that were odd, so half of them. If I want the probability of A and B occurring at the same time, it was 0. There was no overlap. There is never a number that is odd as well as 2 or 4 at the same time. So that's impossible. But if I ask for A or B, well, it would be everything here and everything there. And do I ever accidentally count anything twice? No, there was no overlap that got counted twice here. And so I could take the 2/6 plus the 3/6 and get 5/6. So it's a pure addition using the OR logic if there's no overlap, if the events are disjoint from one another. Where here, I have to be careful. I can't simply add 3/6, 3/6 and get 6 out of 6 because that didn't take into account that there was this non-A or B scenario. All right, so here we go. Compound events. When you consider all the outcomes of either of 2 events, A and B, you form a union of A and B, shown in the first diagram. When you consider only outcomes shared by both A and B, you get the intersection. So that's A and B logic. You get fewer possible cases. Okay? And this is called the intersection. As shown, and if you have, when you consider only the outcomes shared by both A and B, you get the intersection as shown in the second diagram. Yes. Okay. The union of the intersection of 2 events is called a compound event. Okay, and so I can combine those. Union is going to be OR logic when I combine those. OR is going to typically mean addition for us. Okay. Now, to find the probability of A or B, you must consider what outcomes, if any, there are in the intersection, right? Did you end up accidentally counting them twice? If they're overlapping, you end up including those 2 times, and you are overestimating the probability. If the events are disjoint, as shown here, you could simply just add those outcomes together and not worry about the overlap. So disjoint events are also referred to as mutually exclusive. They always exclude one another. A never invites B to their birthdays, and B never goes out to restaurants with A, right? Boom. All right, and so to calculate the probability of 2 events, A or B, so this is, pay attention to OR, this is not the word and. Probability of A or B, if there are 2 events that overlap, you would add the probabilities of A and B together, and then you have to subtract the overlap. Okay, and so that's one of the things you have to be aware of. Now notice that would have worked up here. If I did 3/6, let's see, 3 out of 6 plus 3 out of 6 minus 1 out of 6, then I would have been able to calculate that probability here, right? And so this is what they're saying is I could have done P of A plus P of B minus the probability of A and B. And that's what this will equal. All right. So if I did 3/6 plus 3/6 minus 1/6, it's my least favorite number out of all the numbers. Sixths. There you go. So here's the rule. If there's overlap, if there's not overlap, you don't have to worry about it. Okay, so disjoint, you just simply add those two probabilities. Here we go. Example 1. Card is randomly selected from a deck of 52 cards. What is the probability that it is a 10 or a face card? Now, fortunately, 10s are never going to be... Actually, here, let me write it this way. 10 or face. Because there's no overlap, there's no 10s that count as face cards, then I can just simply figure out what's the probability of getting a 10, add that to the probability of getting a face card. There's 52 cards total, so that's my possible space. All right, so 52, 52. And successes here, there are 4 possible ways I could get a 10, and number of face cards for... Oh, let's see. Oh, 3 groups of 4, that's 12. And so I can just simply add these together. And so I get 1650 seconds is that probability, which reduces to 4/13, which is approximately 30.8%. Right? And so for disjoint events, you just add them. Or means add. What about when there's overlap? Well, let's see. What are we drawing? Probability of a face card or a spade. So this is probability face or spade. Yeah. So this is going to equal, and I'm going to need a little bit more space here. I'll need the probability of face, probability of spade, and then I'll subtract this overlap because I don't want to accident. If I simply add those together, I would have gotten that, and notice this got counted twice. So I subtract the probability of both face and spade. So probability of face cards, and actually when there's a Venn diagram, I've got to be careful. I want to make sure probability of face would include all of it, not I wouldn't be excluding this. So let's see. So that's wait a minute. Okay. Oh man, the way they arranged it threw me off. So there's 4 types of kings, 4 queens, 4 jacks. 4 times 3 is 12 face cards. So 12 out of 52. Probability of a spade. Well, there's ace through 10, which is 10, plus 3, that's 13. Yeah, there's 13 cards per suit. And the probability of both, there were 3 in that category. And so 12 plus 13. Fortunately, these all have a common denominator. 25 minus 3, 22 50 seconds, which is 11/26, which is going to be about 42.3%. Okay, if I didn't subtract this little bit, I would have overestimated, and I would have said 50 seconds, and so I'd be wrong. And so the only distinction between these two problems was this one had no overlap between the events, and this one did have overlap. And so as a result, when you're calculating OR probabilities, compound probabilities, you're going to have to pay attention to those cases. All right, so how about probability of selecting an ace or an 8? That would simply be probability of ace plus probability of an 8. Those are never the same. There are 4 ace cards. There are 4 cards that are 8s. Blah. And so that's 850 seconds. So that's 2/13, which is approximately 15.4%. Okay, no overlap. How about a 10 or a diamond? Well, that would be equal to the probability of getting a 10 plus the probability of a diamond. Subtract the probability of both, 10 and diamond. All right, so how many 10 cards are there? There's 4. How many diamonds are there? Well, that's one of the 4 suits, and there are 13 cards per suit. And how many 10 cards are diamonds? There's only 1. And so I get 4 plus 13 is 17. Take away the 1, 16 50 seconds. That reduces to 4/13, which is approximately 30.8%. All right. So I apologize if you're unfamiliar with cards and decks and whatnot. So hopefully you'll have enough information from this to be able to move forward. Okay, here we go. So example 3. Now this is going to be using exactly the same formula, but this time I'm going to know different components and just use algebra to rearrange it. So out of 200 students in a senior class, 113 are either varsity or on honor roll. Now I don't know how that works. Okay, so you got to be careful. We already have or logic. Now we've got to consider: is it possible that there could be students on both? And then that's what they tell us. There are 74 seniors who are on varsity and 51 seniors who are on honor roll. What is the probability that a randomly selected senior is both a varsity athlete and on the honor roll? And so this sounds like an overlap event based on this. That's what I'm trying to find. But let's set up the formula. So I've got P of A or B is going to equal P of A plus P of B minus the probability of A and B. So let's plug in what I know. 200 students in the senior class. That's going to be my total outcomes. 113 are varsity athletes or on the honor roll. So that's this number right here. Okay, and so I already know the or probability. There's 113 out of 200. Do I know those who are simply varsity? 74 were varsity only. Yep. Do I know how many were just on honor roll? Was 51. And over here, I've got minus P of A and B. I don't know that. I didn't know the number of students who were on both. So now this is just an algebra problem, right? I can take 113, subtract. And I think I would end up, if I subtract this from both sides, I'd get negative P of A and B, so I would just opposite both. But after rearranging everything, I would get P of A and B. So 113 take away 74, take away 51, and then opposite it, I get 12 200ths. So there were 12 that were in both categories, which, by the way, is approximately equal to 6%. So 6% of the 200 students were in both categories. And so you can use this kind of or probability equation to then find other pieces of the puzzle if you fill in what you know and solve for what you don't. Okay, here we go. In example 3, suppose 32 seniors are in the band and 64 are in the band or on the honor roll. Okay, so it sounds like it's going to be the same exact setup. Oh, no, my screenshot trick was actually not helpful. Here it goes. Good enough. Boom. So there's my general form. 32 seniors are in the band. Okay, we'll call that event A. So 32 out of 200 are in the band. 64 are in the band or on honor roll. So that's 64 out of 200. What is the probability that a randomly selected student is both in band and on the honor roll? Oh, wait a minute. I still had this fact up here, didn't I? Okay. I was like, I'm missing 2 pieces of information. What's the honor roll probability? 51 are on the honor roll. And so 51 out of 200. And so what's the probability of the and logic? A senior that is both in band and on honor roll. And so I'm going to do 64, take away 30. Oh, this should be a plus sign. Subtract 32, subtract 51, opposite it. And I will get the probability of both at the same time. So what do I get? 64, take away 32. I get 9, take away 51. I'd get negative 19, and then opposite it. I get that, which is approximately 9.5%. Of the seniors are both in the band and on honor roll. And yeah, they alluded to the fact that by asking that question, and based on the way this other information worked out, I was able to figure it out. Now, if suppose that these ended up subtracting out and getting 0 out of 200, then it would have informed me that there was no overlap. All right, last kind of problem. This is going to be using both let's see, multiplying and adding probabilities. This one's a little bit trickier. Let's see, in the first 4 sections of this chapter, you've learned several probability rules. This one's going to combine some. Ooh, combo. This is the boss fight. Here we go. The American Diabetes Association estimates that 8.3% of people in the United States have diabetes. All right. So population in the United States, 8.3% has diabetes. We'll represent that as 0.083. Okay. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease. Okay, so if diabetes and you have the test, it's 98% accurate that you get the correct diagnosis. And so 0.98 would go here. It's 95% accurate for people who don't have it. And so that's kind of an interesting thing, but that's, so imagine you don't have it, you will get you will get correctly diagnosed 95% of the time. You will be correctly told you don't have diabetes. Okay, so based on this, let's fill out the rest of this information. And so if 8.3% have diabetes, I could do 1 take away that, and I'd find out that 91.7% of the population doesn't have diabetes. For those with it, if it's 98% accurate, that means that 2% of the time it's inaccurate. And for 95% correct for those who don't have it, that means that 5% of the time you don't have diabetes, but are told that you do have diabetes. That would be the incorrect outcome in that scenario. So I've filled out this little flow chart just to kind of like keep track of these things because there's a lot going on. It says the medical lab gives a test to a randomly selected person. What is the probability that the diagnosis is correct? And so I'd be looking at this outcome, right? Or for the tree diagram, I'm looking for this and this. And so I'm looking at this outcome to this outcome and this outcome to that outcome. Yep. All right. And so what would we describe this outcome as? Well, that's the probability that a person has diabetes and that they get the correct diagnosis. That's what this would be describing. I'm also looking for this outcome, the probability that a person does not have diabetes and that they get the correct diagnosis. All right. So this is the answer that I'm looking for. How do I find the probability of A and B? Well, I can multiply those outcomes. Now, those are not independent events. They are dependent. If they were independent, then these numbers would have been the same. It wouldn't have mattered whether you have it or not. The test would have been equally accurate, but they do matter. And so this part can break down the probability of A and B. I can't simply multiply these or actually, oh, no, I can, because this already is a given scenario. But this is the probability of A times the probability of B, assuming A already happened, which is describing that. And so probability of A is 0.083. Probability of B, the correct diagnosis, assuming the person already has diabetes, it's correct 98% of the time. And so when I multiply those, I'd get one outcome. But to that, I have to add this scenario, this branch. And the reason I'm adding these is this is an OR, right? I'm considering a correct diagnosis if they have diabetes and get correct, or if they don't have diabetes and are told correctly that they don't have diabetes. So that's OR logic, which is why I'm adding here. And there's no overlap. I don't have to subtract the overlap because there's no person that both has it and does not have it at the same time. And so what's this? This is going to be the probability of not A, which is 0.917. And I'm going to multiply by the probability of B given not A happened. How often did people without diabetes get correctly diagnosed? That was the 0.95 scenario. So, I'm running out of space. Let's see. Let me multiply this out. We'll take a little intermission here. So this represents 0.08 1. So 8% of the people in the whole population, right, will have diabetes and get correctly diagnosed. And then 0.917 times 0.95, I get 0.871. And so now if I add those together, final answer, the probability of a correct diagnosis is 0.952. So 95.2% of the time, the diagnosis is correct. Let's see. What is the probability the diagnosis is incorrect? Well, the easiest way to do that is just do 1, take away that, right? It's going to be the complement of that event. Although you could have branched through the diagram to be this outcome and this outcome, but those are perfect complements of each other. So 1 takeaway. But I think yeah, I'll leave you to it. This video's been long enough. We've covered every example. Hope you all have a great day. Adios.